Hello everyone. Now I'll present our work on APT, the efficient set-channel analysis framework against the inner product masking scheme. I am the first author, Minjing Dian. I come from the Institute of Information Engineering, Chinese Academy of Science. This presentation is divided into 4 parts, and I will start at introduction and previous work. Set-channel attacks exploit various physical leakages, such as the running time, the power consumption, or the electromagnetic emanations, then to recover the sensitive data of the crypto system. Among all countermeasures against set-channel attacks, Boolean masking is the most widely used for its great performance. Specifically, Boolean masking splits the sensitive values into d+1 shares by XOR. However, its implementation cost is at least quadratic to the number of shares, which hinders the practical use of Boolean masking with a large share number. To strengthen the Boolean masking, several works have suggested performing the masking with more complexity to provide higher order security while keeping share numbers small. Inner product masking is one typical masking scheme. We can see that the cost of 2-share inner product masking is higher than that of 2-share Boolean masking, but lower than that of 3-share Boolean masking. However, as for the security, we can see that the 2-share inner product masking is greatly higher than the 2-share Boolean masking. Then we introduce our efficient framework against the inner product masking. Our framework is shown as a figure. First, we collect the leakage from the target device. Then we make use of leakage and the inputs or the outputs to generate the predicted template. Then we analyze with the predict template and the leakage. To predict a proper template, we introduce an assumption that the leakages are under the Hamming-Weight model, and sigma denotes the standard deviation of the noise. Here is a prediction of extreme values of the leakage under Hamming-Weight model with the help of sigma. Then we introduce how to predict the template. First, we compress the leakage to the interval from 0 to 1. Since the Gaussian distribution is symmetric, only the extremum in one set needs to be calculated. We can obtain the extremum of each Hamming-Weight value. Then we initial the mean vector, then using the extremum values to help to compress the template to the interval 0 to 1 as well. Then the M is a predicted template for the leakage. Then we introduce two analyses, which are maximum likelihood-based analysis and Euclidean distance-based analysis. We can recover the shares error in inner product masking with this analysis. Since the parameter L is public, we can then recover the sensitive data at last. Then we show our experimental results. It can be seen in the simulation that our two proposals are close to the second-order CPA against the Boolean masking scheme. But more importantly, the ED-based analysis outperforms the ML-based analysis and second-order CPA while aiming at the optimal IPM scheme. Here is our experiment setup. The power traces are collected by the chip whisper light boot, and we can see that some outliers are included in these traces. In practical experiments, if we attack directly, it can be seen that the curves of our proposal are not consistent with the results of simulated experiments after 115 traces. And if we remove these outliers, the results are consistent with the simulated results at last. Finally, we conclude our work. In our work, we target on the AES implementation using Boolean masking and inner product masking, and we propose efficient framework to analyze them. Our proposal work since the parameter L is public, so if the L is randomly selected from a elaborated public set, our proposal will fall to work. This is my presentation. Thanks for watching.